Yeah, hi together. Also from my side, Lucas Bo is my name. I'm responsible for the development of automatable wiring harnesses here at BMW in Munich. And I have the honor today to give you a short introduction to the degree of design for automation, or let's say, keep it just short, DDA, which is, yeah, one of the main innovation of the second version of the DIN 72 or 36. And we've learned a lot today already from Mr. Reinhardt and Mr. Kübler that it's all about, yeah, let's say, achieving the transition from the manual to the automated production. And as we've already heard, that it's achieved by standardizing the automated production and its automated production equipment. And let's say on a basis, the requirement is also addressed at us on OEM side is that the harness design, of course, conforms to the standard. So also we have on the harness design a transition, let's say, from the today's design to a design in future that can be produced automated in a most effective and easy way. And for that, to make the daily life a bit easier, with all the relevant stakeholders as OEM and the tiers and the machine manufacturers, our goal was to define a standardized metric that helps us to determine and all stages of the development whether a wiring harness confirms to the standard at the moment, and of course how well, and also gives an impression how well this harness can be produced, hopefully automated in the future. And I've brought the chart with me, and what you can see, I mean, of course, I've highlighted it in red, is that the main focus regarding the manufacturing effort of a wiring harness design is the block loading, taping, and the clip assembly. And what has the DIN 72 or 36 in common with this chart is that also the focus here is on those three process levels. I mean, why is it that way? Because the wiring harness design has the most impact on the manufacturing regarding those three process levels. And that's what also the reason why we kept this focus also regarding the KPIs. So we defined three KPIs regarding the DDA. We defined one for cutting, crimping, pinning, what we also call block loading as total, and the taping, and one for the clip assembly. I will go shortly through them, starting with the DDA-B, B of course for block loading, which is, let's say it easy, it's just the share of core ends of a wiring harness that can be contacted automatically, and of course, because they're complying to the design rules. And you calculate it if you, just take the sum of the core ends that can be automatically contacted, and you put this in the numerator, and in the denominator you have the total number of core ends in the wiring harness. And let's make it easy. Like if you have a connector that is suitable for automated production, let's say this connector has 4 core ends connected into it, then it would just be you take the total number of core ends and subtract 4, write it in the numerator, and then divide it by the total number of core ends. So, and that also, that principle goes through the all the other DDAs. The second one, DDA-T, T for tape, is also here just a description of the share of wiring protection of a wiring harness, and that of course can be applied automatically by complying with the design rules. So here you have in the numerator, you have the DMU length, which you can find in the wiring harness drawing, and you put in here the DMU length, of course, of the wiring uh, harness protection length that complies to the design rules, and divide this by the total length. And the last one would be the DDAC for the fixing parts for the clips. And still the same principle, share of fixing parts of a wiring harness that can be applied automatically by complying with the design rules. So same as at all the others here, we have in the numerator the number of fixing parts um, that comply with the design rules, and in the denominator we have the total number of fixing parts. To make it a bit more practical, we added one, let's say, top level DDA KPI. It's nothing less than just the unweighted average of those three DDI we've talked before, um, just to make it a bit more easier to like have one KPI for one wiring harness. And to make it practical and hopefully understandable, I have one, let's say, fictitious example with me today. I thought about one wiring harness that is shown here in the slide, and I've added some violations to it, and then we can calculate the DDAs, but they're quite easy. So we will start with the DDAB, the block loading one. Um, we have a total 68 core ends in this example, and we have two violations. So one connector isn't suitable for the automated production, and one feed-through grommet is also included here that also is not suitable for automated production. So this would result in, at the connector side, 6 core ends that probably can't be produced automated or can't be contacted in an automated way. And on the grommet side, we also have 4 core ends that have to be open. So we would calculate the DDAB by subtracting the 6 plus 4, which would be 10 in total. We subtract those 10 from the 68 and divide this by 68, and that would lead us to a DDAB of 85.3%. Regarding the um, wiring protection, in my example, I want tape everywhere, so I would tape from connector to connector, and we have a design rule that defines the accessibility for the taping head, which would be 15 millimeters on the one side and 40 millimeters on the other side in total. So we have those 55 millimeters. So we would subtract the 10 times 55 millimeters from the total DMU length, the 2,190 millimeters divided by 2,190 millimeters, and this would lead us in total to a DDAT of 74.9%. And then last one, DDAC for the fixing parts. This one is really easy because we only have 3 fixing parts, 3 clips in total here, and one clip has 2 violations. So first of all, it's not suitable for the automated production. And the second one would be it's moved a bit too far to the left side to the branch, so we don't have the accessibility that we need, which is described in the design rule for the clip accessibility. And this would lead us in 2/3, so a DDAC of 66.7%. And then, of course, we can also calculate the DDA in general as like one main number, which is just the average of all those 3, and that would be then the 75.6%. So this was a real quick overview, and I hope all my explanations were easy to follow. And thanks for the possibility to give us this short introduction into the DDA. Thank you.